So in this video, we're going to be learning the basics of current, voltage and Ohm's law practically. So we're building a basic LED circuit powered by a 9 volts battery. So we have our LED on the breadboard, alright, and this is our resistor, a 470 ohm resistor. Okay, and this is the circuit we just built. That's our 9 volts power supply, our LED and our 470 ohm resistor. And we're using a 470 ohm resistor because we need to reduce the current through the LED to or below 20 milliamps. And from Ohm's law, 470 ohms resistor will let approximately 19 milliamps flow from a 9 volts battery. So let's read the voltages across our circuit. So we place our multimeter probes on the LED pin to read the voltage across it. Note that the placement of our probe with respect to current flow will affect the sign of the value read by the multimeter. It is assumed current flows from positive to negative. So if the multimeter's positive is placed on the negative of the circuit or component, and the negative is placed on the positive, current will flow from the negative probe to the positive probe, and the multimeter will read a negative value. So here we see our circuit and all positive and negative pins of our components. Okay, so I want you to observe as I place my probes and see that if we place our probes accordingly, we would have a positive reading, otherwise a negative one. Now across the resistor we have approximately 6 volts, but in this case it's positive because we placed the probe properly. Okay, so let's actually go to check the voltage across our power supply, especially because we're using a battery, and if it's a battery that has been used for a long time, we might have the voltage to drop from 9 volts. So across the battery we can see we have 8.8 volts. So voltages across a circuit sum up to 0 volts. So if we sum up our voltages using our signs, we would have plus 2 volts, plus 6 volts, minus 8 volts, and if we sum this up, we would have 0. Now this is Kirchhoff's voltage law. To check the current flowing through the circuit, we have to open the circuit and connect our multimeter in series to the circuit, positive to positive, negative to negative. In our case, I placed in reverse again, so the current reading will be accurate but reversed. So we have approximately a negative 14 milliamps reading. From Ohm's law, our 470 ohm resistor, which has approximately 6.8 volts across it, should pass approximately 14 milliamps. So let's place two LEDs in parallel. Okay, so we see across them we have approximately 2 volts each on each of the LEDs, and across the resistor we have approximately 6 volts. Okay, so let's read the voltage across our battery. So across our battery, the voltage across our power supply is approximately 8 volts. If we sum these voltages together, we have 0. Now, when we sum up voltages, we do so across nodes, and in the case of parallel circuits, each pin of the components connect across the same 2 nodes, so they share same voltage. So we read voltages across the LEDs, the resistor and the power supply. To read the current through the circuit, we open the circuit and connect our probes in series to it, and we see we have same current as before when we had just one LED. And that's because our resistor is the component responsible for limiting current flow. And since the resistor itself didn't change value and the voltage across its ends also didn't change, so what happens is the LEDs will have to share the available current amongst themselves since they are connected in parallel. That we can see as I open the circuit of one of the LEDs to read current through it alone. We see we have current of about 7 milliamps flowing through it, which is same for the other LED because they have similar resistance, which will both sum up to be approximately 14 milliamps. Now, the current from the power supply is approximately 14 milliamps, but gets to the node of our parallel circuit and splits through both loads equally, and that's because they have same resistance, and then it combines after leaving the node of both loads back to 14 milliamps. Now this is Kirchhoff's current law. Let's connect in series. For the first LED, we see we have approximately 2 volts. For the second, we have 2 volts too across their ends, and approximately 4.6 volts across our resistor. Note the voltage across our resistor has changed. It has actually dropped, and that's because the voltages must always sum up to 0. If we open the circuit and connect the multimeter in series, we have approximately 10 milliamps flowing through the circuit, and that's because the change in voltage across the resistor has affected the current it would allow through it. So it's important to note that for series circuit, we have same current flowing through the circuit, flowing through all components in the circuit, but we have different voltages across the circuit, and these voltages depend on the resistance of the loads or the resistance of the components we have in the circuit.